All right, so we're going to start out really basic. I promise we'll get to kind of the meat of it in a moment. But for everybody who might be relatively new to frequency analysis, when we're measuring things, we kind of think and live in the time domain. So if we have a train timetable, the train comes at 6:10, 6:30, 6:50, so on and so forth. But when we start thinking in the frequency domain, we want to bin all of these things together. So we start thinking the train comes 3 times per hour. Rather than the train it comes at these specific times, it's the train comes at 3 times per hour. So that's when we talk about time domain, it's, here are these discrete events. When we talk about the frequency domain, it's how frequently these events happen, which when we look at electric motors and inverters, because we're operating in the rotational basis, we have a lot of things happening at a given frequency. We have a lot of things happening periodically. And just to kind of further put some meat behind that, we have the physical world where we might have something like gears or a clock, and these are rotating elements. And these rotating elements, have kind of what we experience daily in sounds or vibrations. If you've ever had like an annoying sound coming from your refrigerator, that's very much something that's happening in time. So we have this time domain, maybe this little sound signal coming. But if we translate to that frequency domain, we see that we have a numeric description of how frequently we're getting, one of these peaks. So how frequently we're getting each peak. So these individual effects in the time domain are all mixed together. While in the frequency domain, we can actually make sense of it. Event A is happening this frequently with this much amplitude. And we can start to understand things like the noise is coming from our refrigerator, or if we're moving into electric motors, how the excitation of the motor takes place. So again, frequency analysis is taking time domain information, binning it into how frequently are these events happening. And this allows us to separate events and identify, sound A is coming from part A, sound B is coming from part B, so on and so forth. We can identify where problems are or where solutions might be. So as many of you might know, electric motors have excitation that's sinusoidal. And I think it's really important to stress that we almost never work in pure sine waves. I'll probably say that a dozen times today. What we work in is a conglomeration of different waves at different phases and different amplitudes. And we push all of these waves together and we get a complex waveform out. And this is a lot closer to the reality we deal with motor excitation. But it's also important because we can take this motor excitation, and this is a very ugly motor wave, I know. But this is coming from a sound and vibration presentation. Fascinating how similar the two are. We can take this kind of complex wave and we can break it into this, I've got this element with this amplitude and this frequency, this element with this amplitude, this frequency, and this phase. And we can break it down into its individual waveforms, which I think is really interesting and an exciting way to analyze these things. So getting a little closer to the actual motors and what the harmonics we're talking about are. So if we take an imperfect sine wave, so we have this square wave with this kind of wavy top and wavy bottom, an approximate square wave. Well, we can break that down into its different frequency components. We can break it down into the fundamental, that's kind of that main carrier wave, and then its subsequent harmonics, which, sorry, struggling to move my, and we can break it down into, we see a third harmonic element, we see a fifth harmonic element, we see a seventh. So we can take this square wave and break it down to kind of this infinite series of sine waves with different frequencies and amplitudes. And again, when we're getting into the harmonica analysis, that's exactly what we're doing. We're taking these kind of pseudo square waves or not perfect sine waves and breaking them up into their individual elements that are a pure sine wave with a frequency and an amplitude. So this is pretty exciting stuff because this gives us tools to do a lot of analysis, and whether these harmonics, these higher level frequencies are causing problems, we can start to mitigate that. Or, as we'll talk about a little bit, we can use some of these things to our advantage. So the harmonics are seen by these AC signals, and they have frequencies and amplitudes.